We're now going to look at integrating products of trig functions. What if we had the integral of sine mx dx or a cosine n, and recall that this is just another notation for sine x to the m dx. So if we were trying to think of an antiderivative, we may think of the power rule, but we got issues with that because we have a function inside and the chain rule would have applied. So it's going to be a little more complicated. So let's look at an example, and first we're going to consider if we had a sine x or a cosine x function raised to an odd power. What our strategy is going to be is we are going to split this up and have cosine to the fourth x and split off one of the cosines, so cosine x dx. Now it's going to become apparent in a minute why we would do that. But first of all, let's remember Pythagorean identity from trig. That says that sine squared x plus cosine squared x equal 1. And we could solve this for either sine squared x or cosine squared x. In this particular case, we're going to solve it for cosine squared x, and that's 1 minus sine squared x. So now what I'm going to do is I'm going to replace this. This is the same thing as cosine squared x squared, and so I'm going to replace the cosine squared with 1 minus sine squared x, and then I need to put the squared on it, and then I still have the cosine x dx. Now how this helped me is I can now do u substitution, and if I let u equal sine x, then du is going to be cosine x dx, and look at that. By splitting that trig function off, there's my du. So this is going to be the integral 1 minus u squared squared du. Now we've got it down to something we can integrate. So I'm going to multiply this out. So this will be the integral of 1 minus 2 u squared plus u to the fourth du. And then go ahead and do the integration. So this is going to be u minus 2/3 u to the third plus 1/5 u to the fifth plus our constant of integration, and then finally replacing the u with sine x. We've got our answer, which is sine x minus 2/3 sine to the third x plus 1/5 sine to the fifth x plus a constant. So now let's summarize what we did. First, we split off one of the trig functions, and this ended up becoming part of my du when I did u substitution. Then we used the Pythagorean identity to change the remaining trig function to the opposite. And what I mean is if we had cosine, we changed it to a function of sine, and if we would have had sine, we could have done the same thing and then changed it to a function of cosine. And then we'll use u sub, and that function that we split off will become part of the du. Now let's look at an example where we have an even power. This one's going to be a little bit trickier because if we split one off, we'd be left with an odd power, and the Pythagorean identity wouldn't let us replace this with the other trig function. So we're going to need a different strategy for this. Do we remember the half angle formula from trig? Basically, it said if you have the sine of an angle divided by 2, it's either plus or minus, depending on the quadrant it's in, square root of the quantity 1 minus cosine theta all over 2. Now we're going to take this identity and we are going to square both sides. And that way that'll take care of our plus minus because it's going to get squared, and it'll also take care of our square root. The next thing we're going to do is we're going to let x be alpha over 2, so we could replace this with an x, and we could replace this then with 2x would equal alpha. So this would be a 2x. And then we will have this formula as this side is a sine x squared, which could be written as sine squared x, and the right hand side is 1 minus cosine 2x all over 2, and another way we could express that is write the 1/2 out in front. So this is going to be very helpful when we started out with a trig function raised to the second power, we now have a double angle, but we've expressed this as a trig function without a power, and we know how to integrate that. Now, we also would need an equivalent formula starting with the half angle for cosine. And if you recall, it looks just like the one for sine, except there's a plus sign. So if we solved it the same way, we'd have cosine squared x equals 1/2 1 plus cosine 2x. So these are two things that we're going to need, and they are identical formulas, but the cosine's a plus and the sine is a minus, and that's a little mnemonic how I remember that. The sine is minus, okay? So what if we have the even powers? How is this going to help us? So what I'm going to do is I'm going to express this as sine squared x squared, and I'm going to use that formula, which was 1/2 1 minus, sine is minus, cosine 2x, this quantity squared dx. Now let's see what we can do with that. Well, we've got this constant 1/2 that's squared. We can square that and bring that out in front, and then have the integral, and we can multiply this out. So this would be 1 minus 2 cosine 2x plus cosine squared 2x dx. Now, how did that help me? Well, I can do an antiderivative here and here, and then this one, I can use this identity one more time and express this without a power. So let's go ahead and do that. So this is going to be 1/4. We'll do the integration in a minute. This is going to be 1 minus 2 cosine 2x, and then plus 1/2 1 plus cosine. I already had 2x and I need to double that, so it's going to be 4x, and then I'll squeeze on my little dx. Now these are all things that I could integrate, so I'm going to do that. So we've got our 1/4 out in front, and integrate here and we get x, integrate here and we get minus sine 2x, because this 2 will be generated when we do the chain rule here. Now this one is a 1/2, so that's going to become plus 1/2 x, and then we have a 1/2 out in front, and we're integrating cosine 4x, so that's going to become plus 1/8 sine 4x, because we had the 1/2 out in front, and when we do the chain rule we generate a 4, so we need the reciprocal of that, 1/4 out in front there, and then plus our constant of integration. So let's see if we can simplify this just a little bit. So these two can combine because they're both x's and give us 3/2 x, distributing the 1/4 through. That will make that a 3/8 x, distributing the 1/4 to the sine 2x term. That will be minus 1/4 sine 2x, and then distributing that to the last term there, I've got plus 1/32 sine 4x plus our constant of integration. So let's summarize what we did when we had an even power on a trig function. We used the half angle formulas to reduce the powers of the integrand, and we actually had to do that a couple of different times. We first used it here on the sine squared, and then we used it again right here on the cosine squared. So we continued that until we got them down to trig functions that were not raised to a power, so that we could perform the integration. So let's see what we can do with the products of sines and cosines raised to powers, and these are going to be a lot of work any way you look at it. But the thing that's going to clue us in as to what to try first still is whether the powers are all even or not, and in this particular case they are. So when the powers are all even, we are going to end up using those half angle identities again. So we're going to replace this sine to the x to the 4th as a sine squared x squared, and then express it using the half angle. So that's going to be 1/2 1 and then minus cosine 2x, and all of that will need to be squared because of this. And then we're going to replace the cosine squared with its half angle identity, and that's 1/2 1, this one's a plus cosine 2x dx. Now, seeing what we could do to simplify this, we have a 1/2 squared, which is 1/4 times another 1/2, so we can put a 1/8 out in front. And then this is 1 minus cosine 2x squared, and so it's going to be easier if we take this and we multiply one of these with this first because they are conjugates, and so the outer and inner terms are going to cancel, and that would leave us 1 minus cosine squared 2x, and then we still have this factor, 1 minus cosine 2x dx. So let's go ahead and multiply that out, and then we'll be ready to see what we can do with the integral. So first will give us 1, outers minus cosine 2x, inners minus cosine squared 2x, and lasts plus cosine cubed 2x dx. Now looking at this term, I can integrate this, I can integrate this. Oh, I could use the half angle formula one more time here and make this a 1 plus cosine. It already was a 2x, so when I double that, that's going to be a 4x. And then how am I going to deal with this cosine cubed? Well, I'm going to go back to the idea of if I've got a trig function, a sine or a cosine raised to an odd power, I can break one off, use a Pythagorean identity on the other one, and use substitution. So I'm going to need to do that as well. So let's go ahead and we'll integrate the first pieces, and then we'll go ahead and figure out this last one that's going to be a little trickier. So I've got a 1/8 that applies to everything, and then integrate 1 and get x, and then minus, this is going to be 1/2 sine 2x because we've got the chain rule applying and we would have generated 2, so we need the reciprocal here. And then here we have minus 1/2, which will be minus 1/2 x, and then the minus 1/2 to this and the antiderivative, that's going to become 1/8 because we're going to have sine 4x generate a 4. We need the reciprocal, but we need to multiply that 1/4 by the 1/2. Alright, so we have this much, and then we still have plus the integral, and we're going to take this cosine cubed and we're going to split off one of those. So cosine squared 2x times cosine 2x dx. Now we're going to replace this with 1 minus sine squared 2x, and we can do u substitution, letting our u be sine 2x, so our du is going to be cosine 2x, but we've got a 2 out in front, dx, because of the chain rule. Now looking to see what we have here, we have cosine 2x dx, but we don't have the 2, so we could put a 1/2 here and get rid of it there, and then we'll be able to replace cosine 2x dx with 1/2 du. So we're kind of working this piece here, and then we'll put it all together with the front. And I still should make a bracket here because this 1/8 still applies to whatever we end up doing here. So with our u substitution, that's going to become 1 minus u squared, and then we can replace the cosine 2x dx with 1/2 du. So du with a 1/2 here. Now we're ready to work the integral, so we're going to have 1/2 is going to be u minus 1/3 u to the third, and then of course we still have our constant of integration on the end that we hadn't put on this problem that'll need to be there. So finally, putting the sine 2x back in for the u, we would have 1/2 sine 2x and minus 1/6 sine cubed 2x plus our constant of integration. So let's leave that, and let's go ahead and take all of this front piece and we'll add it on. So instead of a equal sign, let's make that a plus sign, and the rest of this is going to be, these two can combine to give us 1/2 x, and then we'll distribute the 1/8 through. Well, let's do our 1/8 in a minute. That's going to apply to this whole big thing, and so this is going to be 1/2 x minus 1/2 sine 2x minus 1/8 sine 4x plus this other piece that we have here. And I actually have a couple of terms that are going to cancel. And final answer is going to be 1/16 x minus 1/64 sine 4x and minus 1/48 sine cubed of 2x plus a constant. Let's just summarize what we did with that one first. We had the products of two different trig functions with both powers even, so we used half-angle formulas to reduce however many times we needed to, kept breaking it down until we could do the integration. If one of the trig functions is raised to an odd power, we are going to break off one of those odd powers. So I'm going to express this one as sine squared x cosine negative 2x, the sign that I'm splitting off, dx. I'm then going to use the same strategy that I did for odd powers when I didn't have the product, and I'm going to express this one using the Pythagorean identity. This is 1 minus cosine squared x, and it'll be multiplied by this cosine to the negative 2x, and so that'll leave us the integral of cosine negative 2x. When I multiply these two together, that's going to give me minus 1. And then I still have the sine x dx. Now I'm ready to do u substitution. My u is going to be cosine x, and my du is going to be negative sine x dx. And in looking, I have the sine x dx, so I'm going to multiply the negative over here, and I can replace sine x dx with negative du. So this is going to be the integral of u to the negative 2 minus 1, and there's my du if I put a negative there. Okay, so this is going to be negative. This would be negative u to the minus 1 minus u, and then plus our constant. So resubstituting, this would become cosine to the negative 1 x, and we have to be careful because we don't mean inverse cosine, so actually let's go ahead and express this differently. Let's go ahead and express this as 1 over cosine to the x, and then these two negatives, and make this one a positive cosine x plus a constant. So our final answer, we're going to express this reciprocal then as secant x, and then we have plus cosine x plus our constant of integration. So what did we do when we had the products of two trig functions and at least one of them was raised to an odd power? Then we split off a trig function, used Pythagorean identity, and used that method. Now, that wasn't too bad, but you can see that products of trig functions raised to powers can be a lot of work. So that may motivate us to say, well, can we come up with some formulas or sort of some shortcuts so when we have these powers on these products and we don't have to just keep doing it every time, we can do it once and then utilize that. So we will be seeing that in part 2. But let's go ahead and summarize what we've done. So basically we looked at products of trig functions raised to powers, and as long as when we're looking at this that either m is odd or n is odd, the other one is real, we are going to use the split off strategy. And so we'll split one of those off that's raised to an odd power, and then we're going to use the Pythagorean identity and use substitution. Okay, if both of them are even, then we're going to have to use half angle identities, and we may need to use them more than once until we can get this down to things that we can integrate. Now stay tuned for part 2 so we can come up with some ways to do these maybe just a little bit simpler.